Okay, welcome to the last session of the G. Herbert Stout Awards. For this session, we have Madison Eaton from Elon University. Title is Soil Carbon on Campus, the Impact of Soil Compaction and Land Cover on Soil Carbon Sequestration at Elon University.
Good afternoon, everyone. I know that I'm the thing between you and your coffee break, so don't worry, I will keep my eye on the time. But my name is Madison Eaton. I use she, her pronouns. I'm a senior at Elon University studying environmental science. And today I'm here to present my research project, which is Soil Carbon on Campus, the Impact of Soil Compaction and Land Cover on Soil Carbon Sequestration at Elon University. I'd like to begin with a land acknowledgement. This is a practice that we use at Elon, developed by our Office of Sustainability. And the research was done at Elon University, and we would like to acknowledge that the land that Elon University occupies is the traditional unceded territory of Indigenous peoples and nations, including Ino, Titilo, Shakori, Saponi, and Occaneechi peoples. We honor and respect the diverse Indigenous peoples still connected to this land. Additionally, this land has borne witness to over 400 years of the enslavement, torture, and systematic mistreatment of African people and their descendants. Knowing and critically examining our history and how the collective we got here is vital for understanding our current reality, as well as functioning as an initial step in the process of healing the deep wounds of our shared history. If you're not familiar with the practice of a land acknowledgement, I definitely encourage you to check those out. Here you can see a map of what is currently known as North Carolina and the variety of Indigenous groups that lived here before we did. With that, we'll get into the background of the project. This research was done at Elon University, which is located in central North Carolina. Our campus is 690 acres, and it's very highly manicured and maintained by university landscaping. I chose specifically to study the historic neighborhood, which is the oldest neighborhood of campus, established in 1889. Since the 1980s, there's really been no major construction taking place in this neighborhood, so it's allowed the soils to have the most time to recover from a lot of anthropogenic disturbing of them. Like I said, we very highly value the aesthetics of our campus at Elon, and for that reason, the campus is regularly maintained by landscaping crews 7 days a week throughout the year. They have a big impact on our campus there. Elon has a carbon neutrality goal. We strive to be carbon neutral by 2037, and so I thought that currently, as soils are being drawn more attention to as a potential carbon sink, I thought that through this research, I may be able to contribute to that carbon neutrality goal by using effective landscaping practices at Elon to contribute to our organic carbon sequestration there. The purpose of this research project was really to dive into the role of soil as a potential carbon sink. Like I said, a lot of attention is being turned to soils as we continue to increase our carbon emissions. We want to learn and see more about how we can get that carbon down into the soil. Specifically, I wanted to look at the factors that influence carbon soil sequestration. There are several prior studies that have been done into soil carbon sequestration on college campuses around the world. Several have been done in the United States, as well as a study in India. These studies have focused on land use, which is what is taking place on top of the soil. They've also looked into tree canopy, but several of these studies have pointed to the need to further study soil compaction because this could potentially have an effect on the sequestration processes. So with that, I developed the research questions of, is there a correlation between soil organic carbon or SOC levels and soil compaction, as well as the land cover? And what is the role of soil compaction, grain size, and land cover in the soil organic carbon levels? I came up with the 3 hypotheses. First, that compaction is the limiting factor of soil carbon sequestration, but that compaction would be largely determined by land cover. And finally, that the grassy areas on campus with those clay soils would be the most compact and therefore have the lowest levels of soil organic carbon. GIS was crucial for the development of this project. Mainly, I was using the ArcMap software to create a map of the study area on campus, classifying the different land use cover categories here. So you can see the different colors representing the different types of land cover. Primarily, the historic neighborhood is grassy lawns, so that's what you see in green here. Grassy lawns refers to turf grass, which is kept very short, very green, mowed regularly by the university. Next, in yellow, we have annual flower beds. These are tilled beds that the university plants annual flowers in and replaces those flowers throughout the year. So landscaping says that one of their sustainability practices is by replacing these plants. In the summer, they plant more heat-tolerant ones, and in the winter, they plant more cold-tolerant ones. Next, in purple, you have perennial plant beds. These are beds that are tilled and planted by the university, but they're not being replaced on a regular basis. You have more bushes, trees, and other vegetation and less flowers. In blue, we have mulched beds. These were beds that were tilled and mulched with either wood chips or pine straw, but there was no vegetation growing in them at the time of sampling. And finally, in brown, there were a few areas of bare soil. These were areas where either turf grass had really not taken root, or you could tell that due to heavy student foot traffic, nothing was really growing in these areas, and we decided to pull them out to be their own classification. So using the ArcGIS software, I created each one of these polygons by hand and assigned them the attribute of the land cover type. The study area was over 53,000 square meters, and I created over 30,000 of polygons representing these different land cover types. That leaves us with over 23,000 meters squared of impervious area. That was representative of about 43% of the study area. Impervious areas were those buildings, roads, walkways, any places that didn't have the soil right there at the surface or vegetation. And you can see the breakdown by land cover type here. It was predominantly grassy lawns, about over 67%, followed by perennial beds at over 29%, and then those remaining three categories were much smaller proportions of the study area. Another way that the GIS was extremely helpful in this process was through ground truthing. I was able to, in real time, make sure that my map and the real campus were matching up as well as they could. So you can see two examples here. First, the aerial imagery I was using is from 2018, and there have been a few minor changes to campus since then. You can see several new walkways have been created, and also in 2019, shortly after the aerial imagery, they did build one new building in the study area. So you can see I left that out on my map. But the way that I did my ground truthing process was I went out on campus with a measuring tape. I measured areas that I could very clearly see on the aerial imagery. I wrote those down, and then I headed back into the GIS lab, and I was able to measure my polygons that I have created and compare those two distances. So I went out and sampled several places around the study area that would be easy to see and compared those measurements, and I came up with an overall average error of just 0.4 meters, and I'll be able to take that through the rest of analysis for estimation. I also used the GIS to randomly generate all of my soil sampling sites. You can see here the map of all of the total sample sites. We decided to do the number of sites proportionally based on how much of the study area these land covers took up. So you'll see we had 30 sampling sites from our grassy lawns, 20 sampling sites from our perennial beds, and then we set a lower sample threshold of 10 sites for those remaining three land cover categories. You can see a zoomed in picture of the annual sample sites with the open attribute table as well. I added fields for the latitude and longitude so that I would be able to go out into the field and find these sample sites. We found that the latitude and longitude were only useful up to about 3 decimal places just due to the uncertainty and hard times with the reliability of the GPS device. But between those 3 decimal places, as well as just seeing where I was relative to different buildings on campus, having the map in my hand, we were able to find all of the sample sites confidently, and each got their own unique sample ID. Additional methods: once the GIS map had been finalized, we headed out into the field to do our sampling. We took our soil compaction measurements using a digital penetrometer. This is a device that I would push straight down into the soil, and it would give me a reading in PSI of the maximum amount of force that I had used when pushing down, because that correlates to how compact the soil is. This is just a measurement of how closely those soil particles are together, because that can impact some of the processes taking place in the soil related to carbon sequestration. At each sample site, I took 3 compaction measurements and then found the average of those. When we went into the field, we only ended up sampling from grassy lawns, perennial beds, and annual beds of those 5 categories, because grassy beds and perennial beds were predominantly what was covering the sample area, and then those annual beds we hypothesized to have a big difference relative to the other 2. We made sure to sample more than 48 hours after any rainfall, as well as above freezing temperatures, to make sure that the soils were as natural and undisturbed as possible. At each sample site, I also took a soil core from the top 10 centimeters, and you can see a picture of each land cover type here. The first one that you have is the grassy lawns. You can tell a little bit of turf grass at the top, and then it's really that Carolina clay with that trademark red color. Next, at the top, you've got a sample from the annual beds. These were the most interesting beds to sample from. Visually, you can tell that it looks very different from the grassy lawns. It's much darker in color, leading us to believe that there was a lot more soil organic matter. I could tell from sampling that when I would push the digital penetrometer into the ground, at about a foot or two down, you would hit a hard layer of either clay or gravel. So we think that when the university was creating these beds, they just tilled down about a foot or two and then just filled it in with compost. They're replacing those flowers, like we said, annually, and so they never have that much time to establish a deep root system. So it was also very loosely compacted. And then finally, in the bottom corner, you have an example of a soil core from a perennial bed, and visually you can see that it kind of looks to be a mixture of those two other types in the middle, where you do have some of that red color from Carolina clay, but you also have some of the darker organic matter as well. We have a lot of work still in progress. In order to determine the amount of carbon in the soils, we are completing loss on ignition analysis. We have dried all of the soils in a drying oven, and we will be placing them in the furnace at 400 degrees Celsius. We will be taking the weight before and after, because during this combustion process, what will be burning off is the organic carbon. So the difference in weight from before and after will be representative of the amount of carbon in the soil. We're also doing a grain size analysis to see how susceptible the different soils are to being compact. And then finally, later this spring, we'll be doing electron dispersal X-ray metal analysis to get a full soil profile to see all of the different metals that are present in the soil. Specifically, we will be looking at aluminum and iron oxides because these have been hypothesized to influence that soil carbon sequestration process. You can see here the soil core that we used, as well as the digital penetrometer. Early results, we can already tell that soil compaction and land cover are very strongly correlated. Based on a one-way ANOVA statistical analysis at 95% confidence, the p-value was less than 0.001, saying that this correlation is very unlikely due to random chance. And the effect size, we looked at an eta squared value of 0.910. This is a massive effect size. The threshold for large using an eta squared is 0.14. So you can tell that 0.91 is very much over that threshold. And this is just saying that the difference in those means for soil compaction based on land cover is statistically different. We're hoping to continue and expand this application at Elon. Like I said, we only sampled from 3 of those 5 land covers, so I'm hoping that upon my graduation in May, another student will be able to take over this research project and sample from those remaining 2 land cover categories. We'd also love to expand this to other areas on campus. Like I said, historic neighborhood is the oldest, but we have several new neighborhoods on campus, and we would love to expand this process into those as well. We're also hoping that we laid the groundwork to be adopted by other universities who are interested in looking into their soil carbon sequestration. By using our methodology, this could be expanded to other universities across the country as well as across the world to implement their own GIS mapping of their campus if they want to contribute to their soil carbon neutrality goals as well. But with that, these are the acknowledgements that I'd like to make, especially thank you to the G. Herbert Stout Student Award for the pleasure of being able to present for you all today. And if you'd like to learn more, I'll be presenting at Elon in April about the results of the rest of those chemical analyses. But with that, any questions? Mm-hmm.
So you separated out the bare soil into its own category.
Mm-hmm.
Do you have any, I guess from your ground truthing process, was there any way to tell which specific areas are those bare soil just because the grass didn't take versus the desire paths where people are, where there's foot traffic compacting?
Mm-hmm.
Things to further differentiate that category?
Yeah, I would love to dive into that more. I'd say that the easiest way was how close they were relative to sidewalks. If you've ever been on a college campus, students make their own paths, and that's how you know where the university needs to put a new sidewalk. So a lot of times what we were seeing was in kind of an elbow between 2 sidewalks, that corner part is just bare of grass, and you can tell students are kind of cutting the corner with that foot traffic. So I'd say that the bare patches close to sidewalks were likely due to foot traffic, and then bare patches elsewhere, it just may have been due to not taking root or potential foot traffic as well. You can tell too the standalone patches versus the ones where it's like a continuous path. Great question. Mm-hmm.
So you only stapled the first 10 centimeters?
Yes.
Is there a reason that you didn't go deeper?
Mm-hmm. a great question. There's a lot of different soil analyses that have been done, and in my research, a lot of them focus on the top 10 to 20 centimeters. Specifically, we chose this because of the root penetration of the different things we were looking at. We were really focused on the root penetration and the biological processes occurring in those areas as being responsible for the soil carbon sequestration. So that's why we chose to do shallower, especially with those annual plant beds. There's really not going to be much happening below that, but it would be interesting to expand the study in the future to deeper soil profiles as well.
What about other land cover types that don't exist in this area? I think like forest, for example.
Yeah, that's a great question. So we chose these 5 because they were the ones that occurred in the study area, but Elon University also has a student-run farm as well as Elon Forest. And there's another student who is doing a specific research project into Elon Forest soils. So I'm really excited to be able to compare with him when we're both finished and see what those differences may be. And we'd love to kind of expand this into those other areas as well and see how those may impact it too. Great question.
With the annual garden beds, did you see any variety there? Sometimes having different mulch and yet other elements would affect your carbon sequestration or carbon that would be in the soil.
Yeah, that's a great question, and that's something we want to look into more as well. Usually, Elon is either using pine straw mulch or like wood chip mulch. We initially thought of differentiating between the two, but it just became a little too much with all of the different variables that we had going on. We decided to just do mulched beds as one entity at first, and then hopefully in the future, that would be something really interesting to look into, is seeing if those different types of mulch affected it, as well as exactly which plants are being planted. The annual beds that I sampled from currently just have some flowers in them, but it's something we'd love to continue looking at in the future.
Any other questions? Thank you very much, Madison.
Thank you.